If you still remember that we talked about the uncontrolled half-wave rectifier, which one is the uncontrolled? Yeah, go back and here you are. Half-wave rectifier, we started with R load and then we have RL load. We have a look at the waveforms and equations and derivations. Right, now, anyone can help me? We would like to recall back on the... Can you see my screen?
Okay.
The rectifier by on the half wave. What is half wave? Half wave means you only use one device of the semiconductor. In this case, we would talk about the uncontrolled. We are taking diode as the switching device. So let's start with this one first, then later we proceed with the controlled, yeah, half wave controlled, still half wave. Right. First of all, how to draw the circuit of this half wave? We know that rectifier is actually changing from AC to DC. So the input definitely will be AC as input, and then go through the switch. In this case, the switch would be the uncontrolled diode. And then we have the load. In this case, I will draw a box of load. Because load or the consumption could be R load or RL load. RL means combination of R and inductor. So if it is R load, what happened? If it is RL load, then what happened, right? For the same circuit. This is positive and negative and the current flows. Okay, during the positive half cycle, what happened? It is in the conduction mode and you expect that output has some value. And during the blocking diode or the reverse bias state. Oh, what's going on? All right. During the reverse bias state, no output, yeah? Okay, if it's for R load. What about if we have RL load? Okay, still remember that L basically is inductor. Inductor is a passive component is able that to store and release energy. So that's why what is affecting? It's affecting the current, the output current. The output current may be delayed because of the charges that store in the inductor and being released. Yeah. How do I select this one? No. Okay. I don't know how to play around with this whiteboard. How do I move the whiteboard? Any idea? Oh, I have to deselect this one. Nope. Where's my cursor? Okay, fine. I cannot do anything about it. Oh, I have to press the control button. Okay, good. The space button. Now, anyone can tell me how do I draw the waveforms? Okay, what we're interested is on the waveforms. Let's say that we have the input of sine wave. And then what is the output current? This is the Vs. This is the V out, suppose, and then we have the current as well. I out. Anyone can do it for me? So have a look at the left-hand side circuit. This is uncontrolled because of using diode. So you expect that the output is always following the input, yeah, because we're focusing on the R load first. So the output is what? Let's say this is pi and this is 2 pi. So during the positive half cycle, do we get the output? Yes, because it is forward. And then during the negative half cycle, do we get the output? Nope.
That's wrong.
And
Yeah.
then it repeats, right? Okay, after the 2 pi, and then you have 3 pi if the cycle repeats, yeah? Okay, what about the current? Remember that V equals to IR. If it is just a R load, the current will follow the waveforms of the voltage. So in this case, how do we draw the current? The current will follow, and then it will be 0 for the second half cycle and repeat. Okay, now only the magnitude is not the same, but the waveform not the same. Waveform is always the same. So that is the case for R load. So please label them completely with the VM. VM stand for the maximum peak voltage. So this peak current will get from the Ohm's law calculation. Now, if we change this to RL load, let's go to the right hand side. RL load, what do you expect the waveform to be? Can you draw it? If this is Vs, what about the V out? And we start with I out first. I out, and then you will have V out. And then if it is RL load, still say that we have R and L, then we will need to have the VR and VL, right? Not enough space. Okay, what about VR and VL, respectively? So you see that there are so many waveforms. If you are being tested on that, you should be able to draw them, right? So please remember how to do it. First of all, this is uncontrolled. So when it starts, the current will flow directly. So IL, because of added value of this inductor, let me see the circuit here. If this RL load, let's say that we plus L here. Now, the waveform is still processing as usual, but what is changing? The delay happens because of the inductor. Okay, during the negative half cycle, the inductor is able to release the charge. So you expect that this pi, instead of stopping at the pi, the inductor is still releasing the current, right? Releasing the charges. So the flow of charges is actually current. So you expect that the current is actually delayed a little bit. So with the inductor coming in, the I out is not stopping at pi, but it will go a little bit further. Let's see, that we start with from 0, then instead of falling to the pi, it will be released until further, right? Okay, in this case, it will start again during the second cycle and then repeat until you start at the stopping point. Still remember what is the name for the stopping point here? Start from 0, it stop at, what is the name for this point?
Extinction angle.
the unit will be, the symbol is
Beta.
beta, right? So it's from 0 to beta. Now, having the waveform of the IL, then we can plot again the waveforms of the output voltage. Okay, the output voltage, you can always start with the dotted line of the reference. The reference is always the input. Yes, that is M, yeah? M peak voltage. Okay, so when the current is flowing and then it stop at beta, so you expect the waveform to stop at beta, right? Same. Okay, how's the waveform? We start from 0. Do we stop at pi or we go further? The current is still flowing, right? After from pi to beta, so the waveform is continue until beta. So when you reach beta, because the current is already 0, so there's no more output for the voltage. So it will stop here. So we complete the line. So what happened at the rest of it? It go back to the uncontrolled R load. It becomes 0. So if we compare with the R load, only this part that is not the same. Okay, additional of the negative portion happen. Okay, otherwise it will be just the same. So after that, what happened? It will just repeat until 3 pi, and then it go down a little bit until 3 pi plus beta. So this is 3 pi. This is 3 pi plus beta. This beta is pi plus beta. Yeah. So from here to here is beta. What else? Okay, let's proceed. This is the total. Remember, V out is the sum of VR plus VL. So if we want to look at individually on VR and VL, how do we plot the waveform? And we always know that VR is just a constant resistance, so it will always follow the waveform of the current. So the current waveform is, where's the pi? And 2 pi. So it will stop at beta. Same waveforms, 0, and repeat. Okay, what about VL? Remember what is the equation that we use to express VL? VL equals to L, which is the inductor value, di over dt. Di over dt is the gradient of current. So this current, we look at the gradient. Gradient means the sloped. Okay, slope. Slope, it can be positive slope and negative slope. So if it's a positive slope, we draw the positive half cycle. If it is a negative slope, we draw the negative half cycle. All right, let's draw it. Before we draw it, we have to make the border. Okay, you see this is the peak value. From 0 to the peak value of the current, it belongs to, I have to extrapolate until pi. The peak value is the dotted line here. From 0 to the peak value, we have the positive slope. And from the peak value to the beta or the 0 current, we have the negative slope. Okay, positive slope, you will have sine wave like this. Can you see it? And then negative sine wave, you have this until you finish that. It depends on how big the portion is. If we can complete the half cycle sine wave, then we draw a finish. Otherwise, we just stop at whatever we can draw. Okay, so this is the positive part and the negative part, differentiated by the peak reference point of the current, output current. VL equals to L di dt. And then what happened from here to 2 pi? 2 pi is here. It will be 0. And then it repeats again, okay, the cycle. Are you with me? Any questions so far? If we compare left to right, this is R load on the left-hand side, and that is RL load. So if you see the RL load with the pink color circle here, the additional part is the L contributes to the negative part of the waveforms. Here, the negative part is not there on the R side. This is R only. This is RL. Negative part is there for RL. Negative part is not there for R load. And then we have the extinction beta angle for RL. Here, no beta. It's just stopping at whatever it starts, 0 pi to pi. Okay, that is for the case of half wave uncontrolled using diode. What about if we have half wave and it becomes controlled? If it is controlled, what device that we use? We can control, right? Then we have to use SCR. Symbol of SCR is plus a, this is anode or cathode, okay. Okay, using SCR or thyristor. So if we're using thyristor, meaning that we can control what? Which parameter that we can control? Start point. Okay, what is the name of this start point? Just now the stopping point is known as beta. The start point is alpha. The name of alpha is firing angle, or known as delay angle. Okay, now for both cases, yeah, from the R load as well as for the RL load, they are still behaving the same. But what makes it different is the point of starting alpha. Okay, alpha is the firing angle, and it tells the waveform to start. If the alpha is 0, it will behave exactly as what we have drawn here. But if alpha is not 0, it's some angle, for example, it's 30 degree, right? So it will start at 30 degree. So the line will be starting from 30 degree. What happened from 0 to 30 degree? It becomes 0. Okay, here also it will start from 30 degree apart from 2 pi plus 30 degree, so it will delay 30 degree. So this will be 0, and then the waveform continues. So it looks like this. 0 until pi. Originally, the dotted line is like this, but it's delayed a little bit. Same thing goes to the RL load as well. Okay. Let's talk about how do we do the derivation, right? Okay, let's have a look at this diagram. V out for RL load. How do we derive the V out? So we want to derive this V out, this diagram. How do we start? So V out equals to, we know that the voltage, average voltage, or the DC voltage is always referring to V out or I out. All these we are using integration, okay, just to take the area under the curve. So we start with the derivative, 1 over. The full period of the waveform is from 0 to pi or 2 pi. For this waveform, half wave RL load. What is the T period? Anyone can help me? What is the, what should I put it under the 1 over? 2 pi. So I'm integrating from when to when? From where to where? Starting from? The waveform start from 0, right? So I'm starting from 0, but ending at? Where's the ending point? Does it end at pi or beta?
Beta.
Beta. If it stop at pi, then I'll put it pi. So what is the thing that I should put in the bracket? The waveform, isn't it? And the waveform is from Vs. What is the waveform for Vs? Right? Vm sine omega t. So we put in Vm dot sine omega t. So omega t is the variable. Vm is a constant. So Vm can be brought outside. Vm over 2 pi. So what you have inside is only sine omega t, and you can integrate it. Okay, from there, then you can proceed until you get the value. So please make sure that this working is shown clearly. How do you change from differentiate? No, this is from integration of sine into cos. Should be shown, right? You cannot jump from here, first line, until the last line. In between, if you do not show how the changes is, so it's not considered as the complete answer. So please remember, yeah. Okay, any question you want to ask? Regarding this one also, because the equation is too long, typically if you want to ask or test you on this equation will be provided, but the z, the tau, the theta equation, right, the small equation like this one in the circle and that one in the circle, you need to remember. Okay, so I also have given you in the e-learning on how to use the calculator, because you are allowed to use calculator to calculate the value after you obtain all the small equations. All right, anything else you want to ask? If not, then I will have to continue this one. We talked about the derivation just now. That one is on a very simple direct integration of a sine wave. How do you calculate this one then? We know that the equation for the RMS value is always square root of something in the bracket of squared. Square root of something in the bracket of squared. Now, your homework today is to play around with this integration because it is also part of the assessment, yeah? Then you have to make sure that you know how to do the derivation. So you start with this blue box, and then the first thing that you need to do is to change, because sine to the power of 2 is not easy to integrate, right? We have to change to the equivalent only one power, okay, not to the power of 2. So you can refer to the notes at the bottom here. The power sinus, sine to power, you have sine 2, sine to the power of 2x equivalent to half in the bracket of 1 minus cos 2x. So we have to substitute this equivalent into this bracket. So the power of 2 is gone. So it will become linear, easier. So before that, you can take the Vm squared out. Vm squared is a constant. You can bring it out there. Okay, from here, that is your job. How to integrate this one and how to do, you can split them into two, isn't it? How to integrate them individually. The 2 omega t, okay, what do you get? Remember, you have to divide by 2, right? So until you get this, the workout in between is not shown here. So your job is to complete the derivation. Check your answer whether it's the same with the red color box. Okay, everyone please try. It's important to train it. That make sure you know how to do it as well. Okay, so from the picture that I draw it here, the pink color box, which is not so beautiful, but it's still the same picture. This is for half wave RL load. So RL load here is differentiated by the negative part, which is the shaded red color here, the negative part. Now I'm starting from 0 because I'm using the uncontrolled diode. What happens if I change it to controlled? It'll become like this one. Okay, if I change to controlled half wave RL load, then I'm using SCR. What happened to the output is, instead of starting from 0, now it become delayed. Okay, it become delayed. How to spell delayed? Okay, it starts low later on. So it's starting from alpha value. So from here to here, what happened? It will become 0. Okay, rub it off, 0. Nothing happened. Okay, so the waveform still continue as usual of the VS waveform reference till until it stop at beta. Why is it stop at beta? Because the current already falling to 0. When current falls to 0, beta, everything stops. So if we start from alpha, so you also expect that the current also starting from alpha. So the shape of the current is shown here, the dotted line from alpha until beta. Okay, in the whiteboard just now, I'm using the current as a starting point so that I know that when it start, when it stopped. It start from 0, stop at beta. So the waveform range also given in the same range. Here, we're starting from alpha, stopping at beta. So the range is still the same, right? Any problem? You're just cutting out the piece of cake. So when I cut out this piece of cake, this piece of cake is too delicious. You have eaten it. So once you have eaten it, what do you expect the output? Will it be more or less? You have eaten the cake. So the output will definitely become reduced, less, yeah? So the problem is how much is being reduced and how do I calculate the V out? Any idea? Is it still the same process like this one? You're starting from 1 over 2 pi, integrating it. Instead of starting from 0, what happened? We have to start from alpha. So you have to substitute this starting point 0 into alpha and then ending at beta. The rest is still the same. So then here become alpha and then you continue until you get the output equation, which is slightly different compared to this one. Yeah, because the starting point already changed. So you expect different equation. So this one we talked about it already. This is known as firing angle and the ending point is known as the extinction angle. So, okay, right, this one. We out. You will get this answer here on the right hand side, the first square box here. If we integrate from alpha to beta. Okay, then we can play around with it. If you are not sure whether you have integrated it correctly, you can change alpha to, let's test. If alpha equals to 0, what happened? Alpha equals to 0, what happened? Cos 0, what is the value? Anyone? Cos 0 is 1 minus cos beta. Is it the same with the previous case? Let's check. Not this one, the uncontrolled. Where is the answer? Is it shown in the slide? I'm not sure. maybe not shown here. So you can test here after you integrate this one, get the answer, and then you put it in 0. You should be getting the same answer. We out. Okay, the same thing goes to the average current. You can integrate from alpha to beta of the I omega t. But the I omega t is very complicated equation. As I said just now, you don't have to memorize this box, okay? But you need to know how to find the parameters inside the box. Okay, so you can use this one if it is provided to find the average current. So you will definitely find this case here. Calculate the average current of this circuit. So to find this average current, you need to press calculator of the equation. Okay, that is exactly the example I've given you on using the calculator. So please look at it. Same thing goes to if you want to find the RMS value of the current, then you will have to press longer, I guess, because you have the squared here of the equation. So please try your calculator. Different model, you will use different pressing syntax. Okay, after you obtain the IRMS, you can calculate the power using I squared R as usual. Okay, there will be 2 examples here. Additional information is given here because you don't know the beta value. If you don't know the beta value, you cannot integrate. You can start, but we don't know where to stop. So given here 3.79 radians. So the problem comes in, just now when I do the integration, right? I have the equation, but then if I have the equation with the cos alpha and cos beta or sine alpha sine beta, should I put the value of the alpha in degree or radian? Anyone? Anyone here? Degree or radian?
Is it degree, Doctor?
Degree, but oh yeah, I got the alpha, which is the delay angle. Alpha equals to 45 degree, right? But beta is given at 3.79 radian, beta. So should I mix them or I have to be synchronous?
Need to change it.
Okay, which one should we change?
Beta.
It's up to you, yeah? Now, remember, you are the boss. If you want to take it as degree, you make sure that your calculator is in the degree mode. You are the boss to change. If your calculator is in degree mode and you key in the radian number, so that is your problem. Okay, that is out of my control. Okay, make sure your calculator is in the correct mode. You know where, right, to set the degree or to set the radian. Make sure you know, huh? Otherwise, if you key in everything and you get the different answer. So if you want to make it as a default of degree, then you have to change the 3.79 into degree. And you set your degree in the calculator. How do we change 3.79 radian to degree? Anyone can help? How? That is important, how to do it. Anyone? Nobody here? Very quiet. How do we start? 180 equals to pi, isn't it? And then if you have 3.79, what is the degree? I put it as x, so I don't know what is x. So x equals to 3.79 divided by pi times 180 degree. What should I get? Press your calculator. 3.79 divided by pi times 180. What is the number?
17.15.
17? 217.
17.15.
Are you sure? How come I get 217? Anyone else has calculated 3.79 divided by pi times 180? Correct. 217.15.
Betul.
Betul?
27
Okay, good. So make sure you know how to calculate this one, yeah? It's not shown in the text or the slide also. So try on it. If you want to know the answer, right, you can refer to the textbook at page 90 and page 88 lah. Which textbook? Refer to the course outline. It's actually the textbook by, who's the author? The author is Daniel W. Hart. Introduction to Power Electronic. Okay, the example inside there. Okay. You guys still okay to continue? Because now we need to play around with the circuit by adding in a new friend. That new friend's name is freewheeling diode. Okay, start with FWD. So when you have FWD in, what is the impact to the waveforms here? Just now we said that from R to RL, the difference is from negative tak ada, we don't have negative portion, to some negative portion with the pink color here. Now that if I add in the freewheeling diode, what is the impact? Now, to cut it short, the impact is, can you see it? Note also that the output voltage has no negative part. The negative part, is it there? It's gone. Okay, by adding in the freewheeling diode, the negative part will be eliminated. It is originally there without the freewheeling diode, but freewheeling diode is making a new path or a new way for the current to flow. And at the same time, it blocks the way for the voltage during the negative half cycle, which is why the negative part is being eliminated. At the same time, it makes what? It makes the current continuous. It makes the current continuous. It makes the current continuous. And delete the negative part. So if we look at the previous case here, right? Is the current continuous? Yeah, let's see. We start from 0, going up to the maximum, going rise and falling at beta, and then 0 until 2 pi, and then we up again. This case, do we call it continuous or discontinuous? Anyone can help me with the term of this English? What is continuous? What is discontinuous? A or B?
B.
Why is that discontinuous?
Because it is interrupted at beta.
You're right. Discontinuous means the current is interrupted. And what does it mean by interrupted? when the current touches 0, interrupted. Yeah, how to write? Okay, interrupted. So discontinuous. Discontinuous means the current is interrupted or the current touches 0. Once it touches 0, it is discontinuous. So how to know that it's continuous? So the continuous means this is the waveform of current. The current is always above the 0 line. So you see the current is floating above 0. 0 here, right? So it's not touching 0. So the current is always beautifully floating in the air. So this is known as continuous current. Okay, continuous current. In the previous case, this is known as discontinuous current because the current is touching 0. Once it touches 0, it becomes discontinuous. Okay, so by adding this new friend, which is FWD, freewheeling diode, there are two implications. Number one, it makes the current continuous. From discontinuous, it becomes continuous. Number two, it eliminates the negative part of the voltage. So FWD, you just need to remember, it will bring impact to the voltage and the current. What is the impact to the current? It makes it continuous. And what is the impact to the voltage? It eliminates the negative part. Positive part, no impact. The negative part will be eliminated, gone. It doesn't like the negative part. Okay, remember this one first. Now we have to look at it, why that happens. So if you look at this original circuit, the outer line is the diode, source, and RL load. The inclusion of this freewheeling diode is here in parallel with the load. Okay, now that is called the FWD. Can I call this D1 FWD? No, this is just the power device, the usual one. Okay, the one that you add in on the right hand side here, this one D2, you can call it FWD because they are in parallel to the load. Okay, so what is the implication? We already know that it brings what? The current become continuous. Number two, it eliminates the negative part of the voltage. Let's see what is the explanation here. Half wave with RL load is not continuous. Yes, we have seen it. It stopped at 0 and it has a beta point. So a freewheeling diode, sometimes known as commutation diode, can be placed to make it continuous. All right. How does it make it? You can break the condition of the circuit into two modes. One is conducting, another one is blocking. During the positive half cycle, it's conducting, right? The current flows through the D1 and go to the load and come back, right? So it's represented by the first diagram at the bottom left here. So it behaves like the original circuit, no different. The diode is closed, so the current is flowing to the load, exactly the same. That's why you see that during the positive half cycle, this first box, it looks the same, the voltage and the current. Okay, something changes during the negative half cycle, because when the negative half cycle comes in, this diode will be blocking states, right? So nothing happened. But you see that this diode is there. This one is open, but this one provide the path of what? The current can flows in this direction. So represented by the second half of the right hand side C. Okay. This the circuit at here with the diode, right? So this diode become open circuit because negative half cycle, the diode cannot function. But the D2, D1 cannot function, D2 can function. D2, this is the bottom one is D2. The D2 can function. Why? Because the inductor is able to store and release. During the first half cycle, the inductor is being charged. So it's full already. So negative half cycle, this inductor is able to release energy. No charging, right? So what it do? It will release energy. This is like a battery now. And so the battery will release energy and the current can flow. How the current flow? Through the alternative path by the freewheeling diode here, D2. So D2 become conducting, right? In B, the D2 is not conducting because its original circuit is conducting. But in negative half cycle, D2 is conducting. So what do you get? The current is flowing, right? That's why the current become continuous. Because from the first part, the current is flowing. Negative part, the current is still flowing because the path is there. But the problem is, during the negative half cycle, is there any source working here? On the right-hand side, C diagram, any source? The source is there on the B side, but the source is being disconnected on the C side. That's why the output voltage is 0. The current is flowing because it's released by the inductor, but the voltage is not there. The source is not there. Here you see that the explanation is given here. You can read. In contrast, the normal if we compare to the normal half wave rectifier, the circuit in C does not consist of any supply in the loop. That's why the negative part of the V out shown in the normal waveform will disappear. Okay. In this side, because the supply is being disconnected, so V out equals to 0. So this V out equals to 0, and it provides the alternative path that makes the current continuous. Okay, so there are two things, please remember. Number one, FWD will make the current continuous by having the alternative path for the inductor to release or to discharge the charges. Current can flow. And why the negative part of this freewheeling diode added component is missing, the negative part gone? Because when the freewheeling diode is added and when it's conducting, what happened? The source is being disconnected from the negative half cycle operation. That's why the V out is 0. So the negative part is being eliminated. Rub it off. So you see that the waveform is only half, 0, half. Positive half cycle, 0, positive half cycle, and repeats. Okay, that is the current become continuous. Now, from the current, we can expand further to know the diode current. Diode current, we have D1 and D2, right? So if you add up D1 and D2, basically it's the same as I out. So what we can do is we just analyze it chunk by chunk. What do you mean by chunk by chunk? If you look at this, I can call this a chunk, right? This box is a chunks. So a section by section. You can draw it from pi to 2 pi, 3 pi, etc. So from 0 to pi, who is working? When current is flowing means it's working, right? So from 0 to pi means the positive half cycle. Positive half cycle, who is working? D1. So D1 current is there. D2 is working or not? Open. Open means no current flow. So you know that from the positive half cycle, D1 is operating. That's why this one is following the current. Why follows the current? Because they are in the series. Series, the current is always the same. So it will take the current waveform here, but it will stop from 0 to pi only. From pi to 2 pi, what happened? It is being blocked. So open circuit cannot. So current flow by who? By D2. during the blocking state of D1, D2 is operating. So this waveform is transferred to D2. For D2, first half cycle is 0, then it continues the operation of the I out. So if you draw the dotted line, C is actually the same as I out. So that is I out reference. Okay, we just split it into chunks. Yeah, positive half cycle for D1, negative half cycle for D2 individually. Okay, if we combine both of I1 and ID1 and ID2, we'll get the I out. Any problem so far? With that, we have completed the half wave. Half wave? Not yet. Half wave R and RL only. Both control and uncontrolled. So I hope that you can do your own summary, including the equations and the waveforms and the circuits before we go further, so that you don't have a lot of things to remember later or to understand it. Anything, please ask. This is another story by adding the source in. So we'll continue on next class on Tuesday morning. Any problem so far? Any question?